Hello, hi. In today's video, we're going to be adding some transformations. To start with, we'll need a package called GLM. Now, GLM does not stand for Generalized Linear Model, although it does. In our case, we want OpenGL Mathematics. So we can click into this result, and we have this package here. This is pretty much using the same math library as what is running on the, well, not exactly what's running on the GPU, but the same math library is used to describe shaders on the graphics card, as is used sorry, I'm rambling. So I got caught out by this for a second. Basically what happens is when we load a shader, that shader is compiled into machine language. However, the math library which is used to describe the mathematical transformations is the same as GLM, which is used by C++. Anyway, that aside, so we just go to code and we just download zip or clone it, however you want to grab it. There we have it down there. Awesome. And in our downloads, we grab GLM master and 7-zip. Man, when someone comes along and makes 8-zip, these guys are going to be in trouble. Okay, so we go into GLM and I'm pretty sure, yeah, we can just grab this GLM folder and pop that into our dependencies. So we go back to dev, OpenGL projects, here we are. Remember, it's just a bit too much effort to be renaming this every time, so for the whole thing it's going to be called Stage 1 Windows Test. Whoops. It's okay, it's not a big deal. Then we go to dependencies and we paste this in here. Okay, and everything is set up already. This is a header only library. So now we can go in and start actually playing around with this. So the first thing we'll need is, in order to do transformations, we will need this package, GLM, then it's GTC, matrix transform, awesome. And then there's another thing that we'll need. Actually, I don't see why we can't just leave it like this. Why is that complaining about? No, you can open it. Okay, okay, cool. So let's just run through this. Okay, process input, that is fine. Initialize, that looks okay. Now, these transformations are going to occur in the Vertex Shader. So what do we have? We have our ins. Yeah, and let's alter this a little bit. So let's just get rid of the color and just go position and texture. Okay, and then down here, we are only going to take one bit in. That is the texture coordinates. Okay. Just double checking all of that. Okay, that looks great. So in our, yeah, that should, yeah. Oh no, it's not location 10, it's location 0. See, I'm happy because I found this error now, not later. Okay, so we've got our in variables, we've got our out variables. We also want to declare what's called a uniform. Now, a uniform is applied to every single thing, every object. So we'll go uniform 4-dimensional matrix, and we have a 3-dimensional coordinate x, y, z. In order to, I made a video on this at another point in my channel, but in order to include translations in a three-dimensional coordinate system, we need to extend it to 4 dimensions. So we have x, y, z, and then the last component is just 1, and that is used in translations. Okay, so let's say we want a model matrix. Now what a model matrix does, again, I've gone through this before, is if we take the position and we multiply it by the model, then that maps this position from like a local coordinate to a coordinate in our world space. So let's say we have a box. It's going to be a box in this case. We have a box, and the box has its local coordinate axis, and we want to put the box over there. Well, then we multiply it with a translation matrix to send it over there. We want to spin it, so we spin it. Okay, now as well as this, we want to set things up so that the player is the center of the world. So no matter where the player walks, the world is centered around them. So for this, we will need another uniform 4-dimensional matrix called, actually, let's not worry about that right now. Let's just call this, okay, we're going to need to get things in projection coordinates. So what we do, I'll just put brackets around. We don't need this, but just to emphasize it. First thing we do is we transform our position into world coordinates, and then we multiply that by projection. That maps us into projection coordinates. Now, of course, because of the way that multiplication works, we actually don't need those brackets. I just had those. Okay, so we take the position, multiply that with a matrix, that gives us another vector. Then that vector multiplies with this matrix, and that gives us another vector. I mean, this is standard matrix multiplication. Okay, so that is great. Alrighty. So we read, compile the shader, etc. None of that has to change. So there's something we're going to need. For our projection matrix, we're going to need to track the aspect ratio. There we go. Just double checking my code. Now that looks great. So what did we have before? We had X, Y, Z, red, green, blue, ST. Well, now let's just cut that down to X, Y, Z, S, and T. And I'm going to paste this. I'm going to copy paste this in because there's no need typing this out by hand. So this is defining a cube. Okay, that's looking great. So as you can see, we probably don't want to count this up by hand. So let's go vertices.size, which is the number of things, the number of floats in our vertices set, and then because every 5 vertices make one actual, what is a vertice? Is a bit of data. Every 5 of those numbers make an actual like full vertex description. So take that, divide it by 5. Alrighty. Yep, this is great. Yep, VBO, VAO. We we're just going to have to change some of this a little bit. So now, instead of 8 numbers per vertex, we've got 5 per vertex. So our array vertex buffer should be allocating 5 times. I think we can allocate more, that's perfectly fine. Allocating less will be a problem. Okay. Now what do we have? So position is number 0. Texture coordinate should now be number 1. Yep, there are 2 numbers per texture coordinate description, and that should start 3 numbers in. Okay. Okay, so in a previous video, I was setting the clear color inside this loop. Probably not an efficient way to do it, because that doesn't clear the screen, it just declares which color we want to clear the screen with. So I'm going to add a section out here where we set everything up. We'll declare that here. And we'll also pass in the projection matrix. We really, unless our character is like zooming in and out every frame, we really only need to declare that once. So the way we do this is we say GLM will make a matrix 4. The way we make a projection matrix is with this one, GLM perspective. Now it says here, we take a field of view Y, that's an angle, an aspect, that's the aspect ratio, a near and a far. Now note that we have T. T is a generic type, so this is a template for creating a perspective thing. In this case, the type is going to be float. So our float for our field of view Y is, let's go with 45 degrees. Remember that F on the end declares a float. The aspect was declared area earlier. Okay, the near, let's go 0.1 F, and the far 10.0 F. So anything closer than or further than those distances will not be displayed. That's fine because we haven't got a player object yet, so it's perfectly fine. Okay, so then the next thing we need to do is we need to pass that matrix into our shader. So we will say GL uniform matrix 4. So this is for float. V is kind of vector, so because a matrix is a set of vectors, basically. Okay, so the first thing we have here is the location, then the count. We're going to pass in 1 matrix, so that's 1 there. This will indicate whether we want to transpose. We will not transpose. In some systems, it's helpful to automatically transpose upon upload, and then this pointer here to the value of the thing that we're sending in. So that's the actual matrix. So we need the location. So we go GL get uniform location. And then the parameters for that are the program we're using, which in our case is our shader, and the name. Okay, so it's probably a good idea to actually kind of get this once at the start of the program and never touch it again. I'm not going to do that, because here's another bit of my philosophy. Inefficiency is acceptable in small numbers. As our program scales up, we will absolutely fix this. As a matter of fact, it's fine here because we're only setting this once. I'm kind of talking about the model transformation that's going to happen later. Anyway, okay, so one matrix. Are we going to transpose it? No. And then the actual thing. So I want to just put in projection transform. That won't work. And then I could say, okay, well, if I use the address of operator, will that work? And the answer is no, it doesn't work. So actually what we need is, if we go back to the start, there's a library that helps. That is this type pointer. It's basically what we need. Okay. Wait, sorry. Type pointer? Should be... I think that's okay. We'll find out anyway. Okay, so we want... that's the one. Value pointer. So what that does is we pass in a matrix and it returns a pointer to the matrix. Long story short. Okay, so just for fun, let's double check this. If we run this now, we'll get something interesting. Yeah, that's fine. So the reason for that is that we've uploaded our projection transform, but not our model transform. As a matter of fact, so we want to say, okay, what would it look like if we haven't uploaded a model transform? Chances are that would be the 0 matrix, I think. So if we just run this now, yep. So remember, our camera is at the origin and our box is centered around the origin with no transformation. So basically the camera is inside the box right now. That kind of makes sense. So now let's upload the model matrix. Just grab that from before. Okay, so what are we doing? Well, I'll get to this angle thing later. I'm basically going to use that to spin the cube around. But for starters, let's just get the cube away from the camera. So remember, at the moment, X is left or right, Y is up or down, Z is actually forwards or backwards. So we're going to move this box just backwards away from the camera. And that's fine because we're not moving it 10 units back, so it's not going to be further than our clipping plane. Okay, so then we go get the model location and we pass in a model transform. Okay. We get that. Looks like a cube. It does look a little funky. I'll get to that later. But let's make this more obvious. Let's get the cube spinning around. Now this is a funny thing. By the way this works. So this translate function, the first argument it takes is like a matrix from a set of previous transformations. And the benefit of that is you can kind of stack chain transformations together. So starting this off with 1.0 just creates the identity matrix. And then what we do is we just keep progressively stacking these on. So you would want to think, what have we got here? Okay, so let's take our model transform and let's rotate. Yeah. By an angle of, let's go 2 times our angle, and we'll just, the third axis here, third argument is the axis that we want to rotate around. So because Y is up and down, if we rotate around the Y axis, then we'll be spinning around like that. So we would think that we have the box at the origin, we spin it around its origin, and then we send it to a position. It should be spinning in place. Unfortunately, that's not what we get. So if we run this now, this doesn't make sense. It moves to the position, and then it spins around, even though that's not how we defined the transformation. I think if we wait a second, it might come back. Yeah, it does. See? And this actually, this actually really annoys me because this is not how matrix transformations work. However, it is the way GLM has decided to implement them. Which makes no sense, but I could complain about it forever. So, okay, think about it like this. We send it back from the camera and then we spin it around. Doesn't really make sense, but okay. And now we see something, it's a little easier to see. This is messed up, right? We should be seeing some things in front of other things. And the reason for this is OpenGL by itself just renders stuff, okay? There's nothing fancy, it just renders. So it does not have a way to test which things should be in front of other things. By default, it does not. We can set that up. So we go to set up frame buffer. We're going to set another option here. We'll go enable. Yep, enable the depth test. Great. And then when we go to draw, we're going to, okay, so let's run this right now. Nothing. That's not great. Let's clear the color bit as well as the depth buffer. Okay, so every frame we reset our depth buffer and then we draw. There we go. That's looking nice. Slightly janky, but it's okay. It's okay. It's fine. All right. So That's fun. Let's add some other things. So let's also, and see, we can stack on as many of these as we want because we are stacking them onto the result of the previous calculation. So let's go like this around the x-axis. That's interesting. Cool. Right. So that's it. I mean, this is just an example of how we can do some basic transformations. And yeah, hope you had fun. Bye.